Okay, let's start class. I think we stopped here from last time. So we started talk about the contingency tables. We introduced the probability structures, conditional probability, marginals, and the joint probabilities. And we also talk about some different sampling designs and the study designs, right? Okay, so this one is very commonly used in the medical area, called the sensitivity and specificity in the diagnostic tests, like the COVID test kit. So for these, they all have those sensitivity and specificity information. So what is sensitivity and specificity? So here, let's say, suppose we have a particular disease. So we have the D plus means the true infection. D minus means not infected, there's no disease. The T plus means the test results is positive. T minus means the negative test results. Okay? So the sensitivity is the probability, is the conditional probability for getting the positive test results, given the subject does have the disease. Okay, so this is called the true positive rate. Okay, specificity is the opposite, is the probability of getting the negative test results, given the subject has no disease. That's the true negative rate. Okay, so let's see an example. This is a prospective trial of 232 individuals that complaining of sore throats. Then they give the rapid test. So the true status was determined by the standard method. Okay, but this method is takes longer time, but this one is the rapid test. Okay, so here, so we do know the truth through this standard test, but we want to see the sensitivity and the specificity on this rapid test. Okay, so this is the table. So you can see we have 44 positive and diseased, 4 positive but not diseased. Okay, and we have 19 negative but diseased, and we have 165 negative and not diseased. So the sensitivity is what? Sensitivity is the conditional probability among all the true patients. Okay, the true patient means the subject does have the disease. So here, how many we have disease? We have 63. Is that right? That's the total number. So from this 63, we have 44 got the positive test results. Is that right? So the sensitivity is the proportion of positive test results among these 63 patients. So that's 70%. In other words, this test can give us 70% positive rate among all the diseased patients. Okay, so only 70% will get positive test results, but 30% of the diseased people will actually get negative test results, okay? So the specificity is what? Specificity is the among all the non-diseased. So we have 169. We have 165 are negative. So the specificity is 170 or 165 over 169. So that's 98%. So that tells us 98% of those non-disease subjects will get negative test results. But it has a 2% of chance for those non-diseased subjects will get the positive test result. Okay, so this is the sensitivity and the specificity. Prevalence among the source roads is the probability of having the disease. This is the marginal probability. Okay, so here we have 63 diseased, right? From the 232, so that's 27% in this case. Okay, so this just shows the sensitivity and the specificity and prevalence in this example. Okay? Which these are the very commonly used in the medical science. And also to comparing those classification methods, people also use sensitivity and specificity. Okay. Okay, now let's see the difference for the proportion and the relative risk. Now, let X and Y be binary. Okay. So pi1 is the probability of having Y is 1 given X is 1. It's a conditional probability. Okay. And the pi2 is the probability of having the Y equals to 1 given X is 2. Okay, so both pi1 and pi2, they are about the probability of having the Y is 1. Okay, but the difference is what? Pi1 is conditioned on X is 1. Pi2 is conditioned on X is 2. So that means they are the Y equals to 1 rate, but among different groups. Okay, pi1 is for the group 1. Group 1 means X is 1. Group 2 means X is 2. Okay, so we want to compare the pi1 and the pi2. Okay, and that comparison happens a lot in reality. For example, X1 is smoker, X2 means non-smoker. Okay, Y equals to 1 means getting the lung cancer. Okay, so we want to know the probability of getting the lung cancer among the smoker and among the non-smoker. And we want to compare them. How do we compare, right? So we can compare them through the difference, right? So we can find out the pi1 minus pi2. So that's one way. And another way is, instead of using the difference, we use the ratio. So that's called the relative risk. Okay, so relative risk is pi1 over pi2. Okay, and which one is better? It really depends. It depends on different situations. Okay, for the relative risk, this one is maybe more informative if that disease or that outcome is rare. Okay, then using the ratio may be better. Okay, but sometimes you can output both, present both. Okay, and let's see an example. So Y1 means presence of a certain disease. x equals to 1 is an exposure. Okay, so the pi1 is this one, and the pi2 is this. So that means pi1 and pi2 is about the probability of having a particular disease among the exposed population over a non-exposed population. Okay, so exposure means some risk factor in the environment. Okay, so when the pi1, pi2, let's say pi1 is among the exposed group is 1%, pi2 is 0.1%. Then if we just use the difference, it will be the pi1 minus pi2 is 0.009, which is a very small number, right? But if we use the relative risk, it will be 10. So 10, so that means the probability, the relative risk of getting that disease among the exposed group over non-exposed group is 10 times. Okay? So that is more informative about the exposure effect on the getting that disease. Okay? But if the pi1 is 0.41, but pi2 is 0.401, okay, then the difference is the same as this one. However, when we do the relative risk, it's only 2%. So that means getting exposed has almost negligible effect on the disease status, right? So this just gives you some example for using the difference of proportion and the relative risk. Okay? And actually we have another one that's called odds ratio. Okay, so odds ratio is the same setting as here. So x and y are binary, right? Now this time, odds ratio is based on odds. Okay, so first, what is the odds? Odds is, since y is binary, right? So we can have two possible values. Y is 1 and y is 2. Let's say the success is 1, failure is 2. Okay, so then the pi over 1 minus pi, that's the odds of success. Pi is the here the pi is the probability of getting the y equals to 1, right? Over 1 minus pi, that's the probability of getting the pi equals to 2. So that's the odds of success. Okay, so if pi is 0.5, we have 50% of chance to be successful. So then the odds will be 1. But what about 0.9? Then the odds will be what? Odds will be 0.9 over 0.1. That will be 9. So the odds will be 9. Okay? And so on. So the odds can be greater than 1. It's not a probability. Okay? It's a ratio of two probabilities. And these two probability actually has a relationship. If you add these two probability, it equals to what? It equals to 1. Okay, so that's the odds. Okay, so what is odds ratio? So here the odds only involves in y, only involve in one variable, right? Now we have two variables, right? One variable is the y that shows the disease status. Another variable is the exposure indicator or the group indicator. right? So the x, if we also consider the x, then we can have two odds. Okay, let's say this one corresponds to the odds of success for the exposed x equals to 1. And the denominator corresponds to the the odds of success among the non-exposed one. X is 2. And the ratio of these two odds, that's called odds ratio. Like here. So the odds ratio is this one. And you may ask, we have the difference of proportions, we have the relative risk. Why we need to talk about odds ratio? They are almost the similar informations comparing the pi 1 and the pi 2. Is that right? Difference is through the pi 1 minus pi 2. Relative risk is pi 1 over pi 2. And odds ratio is pi 1 over 1 minus pi 2, or 1 minus pi 1 divided by pi 2 over 1 minus pi 2. So why we need to have so many? So why we need to have the odds ratio here? And you will see in a minute. Okay. So first is odds ratio can directly connect to the logistic regression that we will talk about soon. Okay. So logistic regression can be easily interpreted through the odds ratio. That's one thing. And the second is odds ratio. Remember, we talked about the study designs. Like the fixed row, fixed columns, and fixed total, right? For some of the designs, we can only estimate one type of probability, but not the other. Like here, for this example. What we can do is, since we preset the treatment group and the placebo group to be 50-50, so we can only estimate what? The conditional probability for each group within each group. So the probability of getting the AE, adverse event, in the treatment, we can get that. And also we can get that from the placebo. But we cannot get the conditional probability for the AE equals to yes. Then to see the probability of getting the treatment among the AE is yes. No, we cannot get that. Okay, so this one we cannot get from this table, right? For this one, we cannot estimate from this, but we can estimate this. You see that? That's the fixed row cell. Okay, so that could be a very serious problem, especially when we want to compare the two probabilities. Okay, so when we just talk when we doing the here, when we do this pi 1 minus pi 2, these are conditional probability. Have you thought about, is it these estimable? Can we estimate that from the table? Maybe not. Maybe we cannot estimate that because of the limitation for the study. Okay, right? And so we cannot find the difference of proportions. And also, we cannot get the relative risk because we cannot estimate these two conditional probability. Okay, but that is not a problem for the odds ratio. And you may ask why? Why odds ratio can estimate still needs pi 1, pi 2? If I cannot estimate pi 1 and pi 2, how can I get this, right? So that's the most interesting part. Okay, so the interesting part is which you will see in the next few slides. Okay, odds ratio is probably the most popularly used statistics that compares the proportions because it doesn't limit it by the study designs. So that's a very, very important fact that why people likes to use that. Okay, so it's so amazing. You will see that in a minute. It's very easy to prove. Okay, okay, so this one shows the relationship between the relative risk and odds ratio. So odds ratio and the relative risk can be almost the same when the disease or when the pi 1 and the pi 2 are very close to 0. Okay, why? Because you can easily check if pi 1 and pi 2 are very close to 0. This one is equals to what? Very close to 1. This one also very close to 1. So then it's just the odds ratio will be very close to just the ratio of pi 1 and pi 2. Is that right? So that's the connection between the relative risk and odds ratio. Okay, so when they are very close to 0, this one is almost 1. Okay, so that's equals to the relative risk. So the odds ratio property. So when the odds ratio is 1, that means what? That means the two odds are the same. That's obvious because the odds ratio is nothing but the ratio for the two odds, odds 1 over odds 2, right? So means that. Also means pi 1 equals to pi 2. That makes sense, right? If this equals to 1, that means pi 1 and pi 2 are the same, right? It also means y does not depend on the value of x. And if x and y are both random, then that means x and y are independent. Okay, so that is the conclusion that we can draw when we have an odds ratio is 1. Okay, so the odds ratio does not change when the row and the column variable are switched. So that's the reason that the odds ratio, estimating the odds ratio, does not depend on the sampling designs. So if the data are sampled prospectively, retrospectively, or cross-sectionally, we can always estimate odds ratio, but not necessarily for the relative risk and the difference of proportions. Okay, so that's the great feature for the odds ratio. It actually can be estimated by changing the x and y, switch the x and y. Okay, so how do we estimate the odds ratio? So since x and y are both binary, let's say we have these tables, and these are the counts for the 4 cells in the 2x2 tables. The odds ratio is what? Is the diagonal product over non-diagonal, off-diagonal product. So that's n11 times n22 over n12 times n2. So that's how we estimate. Okay, and if we change the x and y, switch the x and y, it's the same. You can easily check. So now we have the y is 1, right? Then y equals to 2 over this is x equals to 1. This is x equals to 2. Now this one will be what? This, so it's still the same. It's still n11, n12, or n22, right? But this one is n21, and this is n12. And you can see if we do that again, it's the same. So it doesn't change. Okay, so odds ratio is the same if we switch the x to y, y to x. Okay, and this is the proof. So to get the odds ratio, it is this one, right? I think that's very easy to see. Okay, so pi 11 is this one, right? Over what? 1 minus pi 11, right? So this is the odds for the x equals to 1 over this is the odds for the x equals to 2 inverse, right? So that's the odds ratio, okay? And it's this one, right? And we can write it out. That's the probability, conditional probability of y equals to 1 given x is 1 over y equals to 2 given x is 1. Okay, that's the numerator. So is the odds for the x equals to 1. Odds of getting the y is 1 over x is 1. Okay, and the denominator is what? Is odds is over the x is 2, right? Now this is exactly the same as what? You see, that's the good, nice part. It's the same as this one. So what's the difference between these two lines? What's the difference? X and y changes now. I switched x to y, y to x. You see that? Now this time is conditioned on y is 1, x is the change. Okay, it's the same. Okay, why you may ask these are equivalent? I just show you the proof. Okay, so the proof is here. So the let's see. So the probability of y equals to 1 over x is 1. Given x is 1 over y equals to 2, given x is 1, that is equals to this. And this is based on the Bayes theorem. Okay, and then you can easily find out this is equals to this and this. Okay, so this just shows that these two lines are equivalent. So you use the Bayes theorem to write it out, and you can easily see these two are equivalent. So the nice thing for the Bayes theorem is that you remember, so the probability of A given B can be write out as the probability of A and B, right? Over the probability of B. Is that right? And then this one can be further write it out as the probability of Now this time is B given A. See that? Times the probability of A. So you can see using the Bayes theorem, it shows the connection between these two conditional probabilities. But changed A to B, B to A. You see that? That's the idea. So you use the Bayes theorem to here, you can easily see these two are the same. Okay, so that tells us for the odds ratio, the X and Y, it doesn't matter. We can switch to X to Y, Y to X, and it's still the same. So that means if it's row sum fixed, we can only estimate one type of conditional probability, but it doesn't matter. We can still use that to estimate the odds ratio, but not necessarily for the relative risk. Okay, so the odds ratio is, so this is the reason why people likes to use odds ratio. It doesn't depend on the sampling designs. We can always estimate that, no matter what the sampling design is. Okay, so okay, now let's revisit the lung cancer example. So suppose we want to compare the smoker with non-smoker in terms of the proportion who suffered from lung cancer using odds ratio. Okay, so the odds of getting the lung cancer among the smoker group is what? Is defined by this, right? Is the probability of getting the lung cancer given smoker over non-cancer over the smoker, right? That's the odds among the smokers. And this is the odds among the non-smokers. And then the ratio of these two is the odds ratio, okay? However, for this, because of this limitation of the designs, okay? In this design, you see we have preset the number of cancers and number of non-cancers, right? So we can only estimate what? We can only estimate the probability of what? Smoker over cancer. But we cannot estimate the probability of having this lung cancer over among the smokers. This one we cannot estimate, right? So we cannot directly find out these numbers from the table. But it doesn't matter because it's the odds ratio. So odds ratio is cool. So we can change this, rewrite it to be odds ratio is also equivalent to this. Okay, now we can change the xy to xy. Now this odds ratio is also equivalent to the probability of being the smoker among the cancer patients. So the numerator is the odds for the smoker among the cancer patients. And the denominator is the odds of the smoker, of being the smoker among the non-cancer patients. You see that? It's the same. They are equivalent. Because for the odds ratio, we can change the xy. Now, these numbers, we can feel very comfortable to estimate from the table. Is that right? Like the first one, the proportion of the smoker among the cancer is what? So the first one is the proportion of the smoker among the cancer. So we have 709. So the smoker is what? So the first one, we can easily find out is 688 over 709, right? And we can also find that. No problem. We can find from the table. And this one from the table, this one from the table. So we can estimate odds ratio. Okay, and you can do in this way, but the quick way is what? Quick way is it's the using the product of the diagonal, right? So it's 688 times what? 59 times 59. Then over the off diagonals. That's the 21 times 650. And that is the estimate of the odds ratio. Is that clear? So that's very simple to estimate. And it doesn't suffer from, it's not limited from those sampling designs because X and Y can change. Okay, so that's the odds ratio. And how do we interpret? That's very important. Okay, make sure you know how to interpret the odds ratio. So here the odds ratio is about 3. So we can interpret in 2 ways. And you may ask why we can interpret in 2 ways. Remember, odds ratio doesn't matter of X and Y. X and Y can change. So that's why odds ratio can always be interpreted in 2 different ways. One is interpreted based on the X, odds of X. One is based on odds of Y. You see that? Because X and Y is interchangeable. Okay? So the odds, so we can say the odds of developing the lung cancer is 3 times greater for the smokers than the non-smokers. So this is focused on odds of getting the lung cancer, right? Okay, we can also change we can also do it in a different way. Now, this time we focus on odds of being a smoker. So the odds of being a smoker is 3 times greater for those develop lung cancer than those who do not. And you may ask, which one is better? Of course, the first one is better because the first one is the one that we care most, right? Because we are not really care about being a smoker or not. We are care about developing the lung cancer, right? Because the lung cancer is usually the we consider as an effect, but the smoking is the cause. So that's why the odds of developing the lung cancer is 3 times greater for the smoker among over the non-smoker. Is more informative, right? And also makes more sense. So although the odds ratio can interpret in 2 ways, but you don't have to do it in both ways. Choose the one that makes most sense. So that's the art of interpretation. Okay, so interpreting, so in practice, I can easily see this is a good statistician or not. Okay, we all can easily fit those linear regression models, logistic models, right? The ChatGPT can write the code for us. So coding is never a problem anymore because of the AI. But how do you interpret? That's the artistic way. You have to interpret in the most reasonable and clear and make most sense. And that's is really can see this is a good statistician or just a program. If you just use this way to do the interpretation, I know that probably this report is from a programmer instead of a statistician, because he or she doesn't know that this doesn't make much sense. But this one is a much better, right? So interpretation is very important. Okay. Okay, the inference for the odds ratios. The odds ratio is highly skewed to the right. Okay, so think about it, why it is highly skewed to the right. Okay, because you, you can see what is the range of the odds ratio. What is the smallest value we can take for the odds ratio? 0, right? That's the smallest we can take. But what is the largest value we can take? Plus infinity, right? And what is the middle point? Middle point means if the two proportions are the same. Middle point is what? Middle point is 1. When if pi 1 and pi 2 are the same, it's 1. So you can see this is why highly skewed to the right. Because the middle point is 1. The boundary, the lower bound is 0, but upper bound is infinite. So that's why it has to be highly skewed, right? Okay, so it's not difficult to see that. And log odds ratio is symmetric around 0. So if we take the log of the odds ratio, now this time we can change the distribution for the odds ratio from a highly skewed to the right to what? To a symmetric. Why? Because now this time, what is the midpoint? Is the log 1, right? Log 1 is actually 0. You see that? And what is the lower bound? If it's a 0, take the log, then it's negative infinite, right? What's the upper bound? It's still the positive infinite. Now you can see it's symmetric. Okay, so that's why people like to do the log transformation, to do the inference on the odds ratio, because this we feel much comfortable to do the inference because it's symmetric and around 0, right? So we can show that the log odds ratio is approximately a normal distribution with the mean is the log odds, but the standard error is in such a simple formula. Okay, so it's just because the odds ratio is always about 2 binary variables, right? So it's always, let's say the x is, no, this is y is 1 and the y equals to 2. This is x equals to 1 and this is x equals to 2. Okay, so we have n 1 1, n 1 2, and n 2 1, and n 2 2. Okay, so the standard error is this one for the log of odds ratio. Okay, you may ask, it seems like this standard error is very simple. How to get that? It's not difficult to do it. It's if you take our statistical theory course, you know that there's a method called the deltas method. Okay, so the deltas method tell us that, let's say the variance of, let's say, a g theta hat. Okay, so that let's say theta hat is a statistic. G is a function of that. Can be estimated through take the derivative of G to the theta hat. Okay? So take the square. So square of the derivatives of G multiplied by the variance of the theta hat itself. Okay, so that's called the deltas method. Okay, so then you can see we have those odds ratios. You can easily see it equals to what? It equals to the log of what? N11 plus log of N22 minus log of N12 and minus log of N21, right? So that's the log odds. Okay, then what is so the G function is the log here. Using the deltas method, you can easily see this is equals to what? 1 over N11 square, take the square, and the plus 1 over N22, take the square, and so on. Okay, but also we need to multiply by that. What is the variance for this? When we have a large sample size, the count is the expected variance. So the variance and the counts is the same. And you may ask why? Because under the large sample, we know that N1, N2, M21, M22, these are all random. So what is the distribution for the N11, N22? It follows what? Follows a Poisson distribution. You remember? For the Poisson distribution, we have a very nice property. Mean and the variance are the same. Okay, so that's why this variance is N11. So it's times N11. Okay, and do the same thing 1 over N22 times M22 and so on. So you can easily find out it's this one. And that's the variance. Then the standard error is just take the square. Okay, so I'm just briefly go over the proof that we can get this. It's a very simple proof. Okay, it's just based on the delta method and Poisson's distribution for the large sample size. So a large sample confidence interval for the log of odds ratio is this one. Okay, and I believe you still remember how to find out this, right? So this is based on the table, statistic table, you can easily find it. Okay, let's say if alpha is 0.05, then it will be 1.96, right? Okay, so the corresponding confidence interval for the odds is this one. So find the cutoff point for the log odds ratio, and then take the exponential on the cut, lower and upper limit. That will be the corresponding confidence interval for the theta, for the odds ratio. Okay, so the odds ratio confidence interval is not symmetric, but it is symmetric at the log scale. Okay, I mean symmetric is because at the log scale it's symmetric around the log odds ratio, but in this one it's not. Okay, because we take the exponential. Okay, now let's see. So in this example, we get the standard error, right? So the 95% large sample confidence interval for the log odds ratio is this way. So this is symmetric around what? This is what I mean. This is symmetric around 1.09. Is that right? This is the center. So that's what I mean symmetric, around 1.09. But this one is not, because it takes exponential. Okay. Okay, so the large sample inference setup is X and Y, both binary. We have these data, right? So we can estimate suppose we can estimate the conditional probability for the Y equals to 1 over X equals to 1. So that's N11 over N1. N1 is the row margin counts, okay? The first row counts, and this is the second row, okay? So P hat 2 is the conditional probability for Y equals to 1 given X equals to 2. That's N21 over N2, okay? Then we want to compare the conditional probability, the P1 hat and P2 hat, okay? And we can use the risk difference, we can use the relative risk, and we can use the odds ratio. These three, okay? And we can, for the odds ratio, we've already talked about the large sample inference, right? But now this one talks about the large sample inference for the difference and the relative risk, okay? So for the difference, that's the standard error. And for the log of the relative risk, it's this one. And similarly, these formula are also from the deltas method. Okay, if you're familiar with the deltas method, you can easily prove that. So the large sample confidence interval for treatment difference is using the difference approach is this one. Using the relative risk approach is this one. But remember, this is for the log of the relative risk. Okay, so if you want to have the confidence interval for the relative risk, you have to take the exponential on both, on the lower and the upper limit. Okay. Now let's see an example. So this is the myocardial infarction study. So in this clinical trial, the participants are randomly assigned to the placebo and treatment group. Okay, so then the subject are followed prospectively for 5 years to determine whether or not an MI, that's the heart attack, occurred. Okay, so overall probability of heart attack is very low. So this is a rare event. Okay, only 1.33%. So here, this is the data. And we want to compare the heart attack rate between the two groups, between the placebo group participants and the treatment group participants. Okay, so the null hypothesis, the pi1 and pi2 are the same. The alternative is they're not. Pi1 is the heart attack rate among the placebo, and the pi2 is heart attack rate among the treatment group. Okay, so we can, from this data, we can find out this is the risk difference, just the pi1 hat minus pi2 hat. We got this. The standard error is here. The z statistic is 5.0. Okay, and we can also do it using the relative risk. And the z statistic is here. Odds ratio is this, and the standard errors, and it's here. So using all three approach, the conclusion is the same because the z stat is much higher than the threshold. So that means what? So that means there is a significant difference between the placebo group and the treatment group in terms of the heart attack rate, right? So which one is higher? Of course, is the placebo group, right? And this one is much lower, okay? And not much lower, it's significantly lower. So interpretation, so the risk difference has the interpretation that the excessive risk of a heart attack on placebo group is 0.0077. Okay, so that's the estimate of the difference. So that means we expected 77 more heart attack in 10,000 placebo subjects than in 10,000 treatment subjects. Okay, so that's how we interpret through using the risk difference. Okay, relative risk is using the ratio. It says the relative risk has the interpretation that individuals on placebo has almost twice the risk of a heart attack than the individuals on the treatment group. Why? It's because the relative risk is 1.8, is about twice, right? For the odds ratio, it's almost the same. And that is because this is a rare event. As I said, if it's a rare event, the odds ratio and the relative risk, they are about the same. Okay, so we can say the individuals on the placebo group have almost twice the odds of a heart attack versus no heart attack than the individuals on the treatment group. Okay, so that's the interpretation based on the odds ratios. Any questions? Okay, this is doing the to compare the pi 1 and pi 2, not using the z-test, but using the likelihood ratio test. We can also do the hypothesis test through the likelihood ratio test. Remember the general likelihood ratio test statistic is defined by the -2 log of the maximum likelihood for the parameter under the known over the maximum likelihood under the parameter are not restricted. So the MLE of the pi under the null hypothesis is this one. That's the pooled estimate of pi. Okay, and you may ask, why is this one? Because what is the null hypothesis? Null hypothesis says the two pi's are the same. Okay, if these two pi's are the same, how do we estimate? Of course, we should pool the data. So we have Y1 events happened in the group 1, Y2 in the group 2. So what we do is we just combine these over N1 plus N2, right? So that's the pooled estimate. And you can prove that, okay? I have already shown you the MLE proof for the binomials in the chapter 1, right? So you can use this, do it in the same way, and you can see that. So the likelihood ratio test study is this one. Okay, so we have 2 by 2 tables. Okay, so I has 2 rows, J has 2 columns, right? So it's Nij times log of Nij over mu hat Ij. So Nij are the observed counts in J's row, in I's row, J's column. And the mu hat Ij is the expected counts for the I's row, J's column. Okay, so what is the expected? Expected is, since this is the MLE, right? So the expected counts is the N1 times the pi hat, times the MLE. Then mu 1, 2 is this one. And the mu 2, 1 is this, mu 2, 2 is this. Okay, so these are the expected, how we calculate the expected counts. Then we can run the likelihood ratio test. Okay, so the likelihood ratio test statistic G square measures the weighted discrepancy between the log of observed and the log of expected counts, right? The weighted means the weights is the observed counts, okay? This is the ratio for the observed and the expected. So if the null hypothesis is true, then these two are very close. Is that right? If the null hypothesis is true, these two will be very close. What we expected is just, or what we observed should be very close to what we expected, if the null hypothesis is true. Then the ratio will be close to 1. So the log of the close to 1 is close to 0. So this will be a very small number if the null hypothesis is true. If we have a very large value on the test statistic, on G square, then that indicates the null hypothesis is probably not true because these numbers are too large to be true, right? So then we should reject the null hypothesis. Okay, so that's the likelihood ratio test. And this is the R code to do the likelihood ratio test for the heart attack example. And you can see the G square is 25.37, okay? And a very large number, and the p-value is very small. So it have the same conclusion, okay, as these. And also the test statistics are very close. Why? Because you can see the z-test is 5. But for this one, its chi-square is 25. And remember, for degree of freedom is 1. The chi-square with degree of freedom equals to 1, right, is the same as the z square, right? So here, for the z, we have 5, but for the chi, we have 25. So, okay, so that is equivalent. So that means using the likelihood ratio test give us very similar results as using the relative risk or the risk difference or the odds ratio. They all 4 give us very close results. And we can also do another one. That's the Pearson's chi-square. Okay, so the Pearson's chi-square is, this is the formula, and it also measures the discrepancy between the observed counts and the expected. Okay, but using a different formula, and also very close to 25, right? So these are the tests that that you can use to test the pi 1 and pi 2s. Okay, when the x and the y's are binary. Any questions? Okay, so far we talk about the hypothesis test to test the null hypothesis is the pi 1, pi 2 are the same against not the same, right? So how about we now this time we test independence between the x and y. Okay, so which is also can be more general, not just 2 by 2. Okay, let's say we have I rows, j columns. Okay, and we want to test the x and y are independently associated to each other, or they are strongly associated to each other. Okay, so if x and y are independent, that means what? That means the probability of having the x equals to I and the y equals to j is the same as the probability of x equals to y times the probability of y equals to j. And you may ask, what's the difference between these two? This is a joint probability, right? But this one is the margin of the probability on x, on y, and then multiplied. Okay, so these two are the same. Okay, or we can write as pi ij equals to pi I plus times pi plus j for all the I and j. Okay, so this is the definition for the independence. Okay, so based on the independence, it also implies the conditional probability at each column and the conditional probability at each row are the same. Okay, and you can easily check that. Okay. Okay, so for testing the independence between the two categorical variables, we can use the Pearson's chi-square test, and also we can use the likelihood ratio chi-square test. Okay, so for the Pearson's and the likelihood ratio, the test formula is the same as before. So the first one, the left one is for the Pearson's chi-square, and this one is for the likelihood ratio test. Okay, but here I put the 2. It should be changed to the capital I and capital J because it's more general. Okay, so let's just change that to capital I and the capital J. So this one is, instead of 2, you should change it to the J, capital I, and the capital J. Okay, so that it will be more general. So the only difference, so then you may ask, wait, so this, if we use the same formula, so it will be the same. So what's the difference between these results and these to testing the pi 1 and pi 2 are the same? And the difference is that is at the expected counts. When they are independent, the expected counts that we calculated is different. Okay, so how do we calculate the expected counts? So we can calculate the expected counts through the row sum and column sum. Okay, so if x and y are independent, remember we have the pi ij equals to pi I plus times pi plus j. Okay, remember I talked about the marginal probability, conditional probability, joint probability last time, right? So this is the marginal probability for the row, and this is the marginal probability for the columns. Okay. So these, based on the definition for the independence, it implies the expected counts for the ith row, jth column is what? Is the ith row sum times jth column sum divided by the total number, n. Okay, you can easily show the expected count is equal to that. That's how you find out the expected counts under the independence assumption. Okay, so then we can do the chi-square test using these formulas. So these are observed counts, that's no problem. But for the expected, we should use this formula. Okay, so what is the degree of freedom? The degree of freedom is I-1 times J-. And you may ask why it's I-1 times J-. And you can easily check. Okay, so here I listed the proof. Okay, so the proof is in 3 steps. Okay, from these 3 steps, you can see, oh, it is this. Okay. Okay, now let's see an example. This is the gender gap in the political affiliation example. So this is from a year 2000 general social survey. So we have 2 rows for the gender, female and male, but 3 columns. That's for the party identification, the Democratic, Independent, and the Republican. Okay, so the total sample size is 2,757. Okay, so let's say the gender is independent with the party identification. Okay, so let's say the party identification and gender, these 2 factors are independent. Then we can find out expected counts, right? Let's say for the female Democratic, what is the expected counts? It's this one. How do we find out? It's very simple. That's the first row, first column, is that right? So you go to the first row sum. That's 1557. You see that? 1557. Then you go to the first column sum. That's 1246. That's 1246. You multiply these 2s, then divide by the total sum. And you got 703.7. That's the expected. And similarly for the male, let's say for the male independent, how do you get the 246? You go to the row sum, that's the second row sum, right? That's 1200. You go to the column sum, that's 566. Multiply these 2 together, then divide by the total sum. Okay, so then you can find out. I would like to mention that last year when I teach this, I asked the student, and most of students said, yeah, it's very simple. Then actually in the exam 1, I have 1 question, very similar tables. To be honest, 80% of the student cannot find the answer. So it's very, that actually proved my observation over almost 20 years in the teachings. Okay? And I always warn the students that when I teach something and I go over that, it's much So you understand these, that's one story. And if I ask you to do it by yourself, that's a totally different story. So when I talk about this, or this number multiplied by that, divided by that, if you follow that, oh, it's very straightforward. There's no problem. But if I give you that example in the exams with the time limit, you are very likely that you cannot work that out properly. Okay, so that's why for the homework, like the homework 1, and I will assign the homework 2 later. Although I just picked a few, if you have time, just work out all the exercise problems. Do more practice so that you will have a much better understanding of how to do that. Because if you really work on the problem, work on these numbers by hand, you will have a much better understanding. And that having this experience can guarantee you that if you see a similar problem in the exam, you should be able to do that. But if you understand what I said in the lectures, that does not guarantee you to work out the problem in exams. And I can assure you, and I see that many years, and so many students think, oh, okay, I know what you talk about. I totally understand in the lectures. But when they work out in exams, they feel just like nuts. They cannot work out most of the questions. And that happens so many times. Okay. Let me stop here, and we're running out of time, so I will pick up from here next time. Any questions before we dismiss? Okay.
So, excuse.
Yeah.
All right. So, if I should understand what you just said, so